Small, weighing less than 0.7 ounce, yet powerful enough to erase pencil marks that may have existed for hours. For generations, this tiny rubber eraser has quietly served as a bridge between the human mind and creativity, accompanying millions of people at desks, in classrooms, and across countless moments of thought. That journey begins with milky white drops of latex slowly flowing from the bark of rubber trees, then passing through a precise sequence of mixing, rolling, heat pressing, and shaping. A refined industrial process that transforms a natural material into a finished eraser. The Factorin invites you inside the world of rubber erasers, a small, everyday object that has stood beside first pencil strokes, unfinished drafts, and countless ideas taking shape. Rubber erasers first appeared in 1770, when British chemist Edward Nairn discovered that natural rubber could erase pencil marks more effectively than any material used before. However, these early erasers quickly revealed their limitations. They deformed easily, their elasticity changed over time, and their erasing performance deteriorated noticeably with use. The real turning point came in 1839, when American inventor Charles Goodyear discovered the process of vulcanization, treating rubber with heat and sulfur to make it stable, durable, and capable of retaining elasticity over long periods. This breakthrough laid the foundation for industrial-scale eraser manufacturing, transforming what was once an experimental novelty into a standardized tool for education and office work. Today, hundreds of millions of industrial-grade erasers are distributed every year to schools, offices, and design studios around the world. And that journey begins at what seems like the most straightforward step: collecting the first milky drops of latex drawn from the trunk of a rubber tree. As dawn's first light filters through the canopy of the humid tropical forest, rubber tappers begin their daily harvest. With practiced precision, they use a sharp knife to cut a thin, slanted groove, about 30 to 45 degrees, across the bark of the tree, allowing the milky latex to flow smoothly without damaging the inner wood. Each incision must be deep enough to reach the latex vessels, yet gentle enough to keep the tree alive and productive. A skill refined through years of experience passed down from one generation to the next. From that careful cut, the white latex begins to drip rhythmically into small collection cups placed beneath the bark. The Hevea brasiliensis, known as the rubber tree, quietly releases this precious fluid, the foundation of billions of rubber products used around the world. After about 3 to 4 hours, each cup fills with 7 to 10 fluid ounces of latex. Once the collection is complete, workers carefully pour the contents into stainless steel containers scattered throughout the plantation, marking the first step in the long journey from forest to factory. Immediately after harvesting, a small amount of ammonia is mixed into the latex to prevent natural coagulation. The compound stabilizes the pH level and inhibits bacterial growth, keeping the latex fresh and elastic during transport. From the remote forests of Southeast Asia, sealed steel tanks filled with latex are transported by trucks and cargo ships to processing facilities. After being transported from the forest to the factory, natural latex enters the compounding stage, a precise chemical process designed to transform the milky liquid into a stable, high-performance material. Inside the laboratory, technicians carefully mix additives first to increase tensile strength, enhance elasticity, and ensure the latex adheres evenly to molds during the dipping process. Only afterward is dye added to achieve the desired color tone. Every formulation is meticulously controlled, as even a few % deviation in the mixing ratio can alter the smoothness, flexibility, or durability of the final material. Once the dry components reach their optimal proportions, a carefully measured amount of vegetable oil is added. This oil increases flexibility and allows the material to glide smoothly during use, directly influencing the eraser's tactile performance. The entire mixture is then fed into a closed industrial mixing system, where the rubber is kneaded continuously for approximately 5 to 10 minutes at a temperature close to 165 degrees Fahrenheit. This temperature range is high enough to soften the rubber and evenly disperse the additives, while still preserving the stability of the material's internal structure. From the refined rubber blocks, the compound is fed into a rolling mill, where it continuously passes through massive heated rollers. Under controlled pressure and temperature, the material is flattened into uniform rubber sheets, typically ranging from approximately 0.2 to 0.8 inches in thickness, 20 to 40 inches in width, and about 3 to 6.5 feet in length. These dimensions do more than define the physical size of the material. They directly influence the rubber's elasticity and the contact behavior between the eraser and the paper surface. This is a critical stage in the process, the moment when the tactile feel of erasing begins to take shape, long before the material reaches its final forming and cutting steps. Once the rubber sheets have stabilized in shape, the material is transferred into forming molds. Here, under controlled mechanical pressure, combined with heat at approximately 240 degrees Fahrenheit for nearly 20 minutes, the rubber reaches an optimal state, soft enough to lift graphite cleanly from the page, yet firm enough to preserve the paper's smooth surface. Any excess rubber is then trimmed away, after which the still hot blocks are rapidly immersed in cold water at around 70 degrees Fahrenheit. This sudden cooling locks the material structure in place, stabilizing its final texture and mechanical properties before it moves on to the next stage. Once the rubber sheets have completed the thermal pressing stage, the material is fed directly into an automated cutting system. Moving along the conveyor belt, the smooth white rubber sheets are guided straight into a mechanical cutting assembly, where sharpened steel blades operate in a steady rhythm, slicing the material into rectangular blocks with precision measured down to fractions of an inch. This process runs continuously, without interruption. Each cut must be decisive enough to produce clean, straight edges and flat surfaces, while leaving the internal rubber structure intact. If the cutting force is too strong, the eraser's edges will chip. If it is too light, the surface will appear uneven, directly affecting how the eraser feels in the hand during use. For this reason, conveyor speed, blade pressure, and cutting timing are tightly synchronized and constantly controlled. The familiar rectangular shape of an eraser is not a random design choice. After cutting, the blocks drop gently onto the lower conveyor, aligning into orderly rows as they move forward, ready for the next finishing stages of production. At a steady operating pace like this, the production line can process approximately 220 pounds of heat-pressed rubber per hour, equivalent to nearly 26,000 erasers per day. At this stage, the material has almost reached its final form, a small, everyday object, shaped with industrial-level precision. After being cut with precision into their final shape and standard dimensions, the erasers continue moving along the conveyor belt into the labeling and surface finishing stage. On the automated line, each eraser is guided into mechanical positioning trays that hold it firmly in place, ensuring the label is applied in the correct orientation and at the exact intended position. Pre-printed paper labels or wrap labels, bearing the brand name, product information, and technical standards, are fed continuously from large rolls. These labels are then gently pressed onto the surface of the eraser by a precisely calibrated mechanical pressing system. The applied pressure is carefully controlled, strong enough to secure the label firmly in place, yet light enough to avoid deforming the rubber material beneath. In modern factories, this entire process is governed by sensors and synchronized control mechanisms. These systems ensure that every eraser passing through the line receives a label with consistent alignment, uniform tension, and a smooth, flat finish, maintaining visual consistency across millions of identical products. The finished products are then packed into cardboard cartons, sealed with industrial adhesive tape, and marked with batch codes to enable traceability throughout storage and transportation. From this production line, millions of erasers are shipped out each year, supplying schools, offices, and creative workspaces across East Asia, Europe, and North America. But the remarkable journey of rubber does not end here. Beyond the familiar shape of an eraser, rubber takes on a completely different form, thinner, lighter, and far more dynamic. This is where rubber becomes balloons. Before thousands of molds are mounted onto the production line, each one must undergo a preliminary latex testing stage. The molds are individually dipped into liquid latex, forming a thin, even coating that must be perfectly smooth and free of defects. This trial step allows technicians to assess surface finish and adhesion quality, ensuring that during full-scale production, the latex will coat each mold uniformly, without wrinkles, thin spots, or imperfections during the subsequent forming process. Only when a mold passes this test does it earn its place on the line, ready to shape rubber into its next form. The molds are meticulously prepared, cleaned, coated with release agents, and inspected to ensure a flawless surface. Now the production line moves into its rhythmic cycle of dipping and vulcanization, the stage where each latex balloon takes on its shape, strength, and elasticity. Inside the factory, hundreds of ceramic and aluminum molds glide slowly along the conveyor, moving in perfect synchronization like the steady breathing of a colossal machine. As the array of molds descends into the latex tank, the surface of the colored compound shimmers like a liquid mirror. Depending on the intended product, the latex may be tinted in soft pink, sky blue, vivid red, or bright yellow. Each hue carefully balanced with latex-soluble industrial dyes to maintain the material's adhesion, elasticity, and chemical stability. Each mold is lowered into the tank at a precisely programmed angle and speed, allowing the thin film of latex to coat every curve evenly. The dipping time and viscosity of the mixture directly determine the thickness of the rubber layer. Just a few seconds too long, or a slight change in fluid consistency, can make the film too thin or uneven. Next, the neck of each mold passes through the beading roller, a rotating system that gently curls the still wet latex around the rim, forming a thicker ring at the balloon's mouth. This signature collar not only makes tying easier, but also reinforces the seal, ensuring airtight performance once inflated. Immediately afterward, the molds are lowered into a hot water bath maintained between 158 and 194 degrees Fahrenheit, where the latex undergoes vulcanization and molecular stabilization for approximately 10 to 20 minutes. In the gentle haze of rising steam, the long chains of natural rubber molecules begin to cross-link, strengthening the structure and enhancing the balloon's ability to retain air, transforming liquid latex into a durable, elastic form ready to take flight. When the vulcanization process ends, after about 20 to 30 minutes, the latex reaches the required elasticity and strength, ready for demolding. Compressed air is then used to separate the rubber layer from the mold and move it onto a drying conveyor. Keeping its shape intact without tearing or distortion, a gentle stream of air is injected inside each mold, creating enough pressure for the cured rubber to lift off smoothly. The balloons slide off the molds gracefully and drop onto the conveyor, where hundreds of pieces are gathered and sent through washing tanks and drying chambers. This entire sequence is fully automated, ensuring every balloon comes out clean, uniform, and ready for the next stage of quality inspection. Freshly separated from their molds, the latex balloons still carry a fine layer of nitrate salts and chemical residues from vulcanization. The production line moves them straight into the washing zone, where clouds of hot steam drift through the air, wrapping the factory in a faint mist. In that warm haze, each balloon spins gently, its transformation from raw rubber to finished product nearly complete. Here, the balloons are immersed in hot water maintained between 158 and 176 degrees Fahrenheit, a temperature high enough to dissolve every trace of residue. Once their surfaces turn smooth and clean, they enter the drying chamber, where heat between 212 and 230 degrees Fahrenheit finalizes the structure of the rubber. This stage strengthens the molecular bonds, giving the balloons greater elasticity and resistance when inflated. Inside the chamber, thousands of balloons rotate slowly in a controlled stream of warm air. Under the steady rhythm of the machines, the rubber sets, the forms stabilize, and the familiar, weightless perfection of a finished balloon finally takes shape. From the drying section, The balloons move into decoration. Robotic arms use pad printing to press colorful logos and patterns onto the smooth latex, turning each one into a vibrant canvas ready for celebration. Once the ink dries, they pass through inspection lines equipped with optical sensors and air pressure gauges that test film thickness, air retention, and color consistency. Selected samples undergo a burst test, inflated until they reach their pressure limit, ensuring every balloon is strong, elastic, and safe. Only those that pass are packaged and prepared to bring color and joy to the world. After passing inspection, the balloons move to the final packaging stage. Workers carefully check each piece by hand before sending them through automatic counting and weighing systems. Dozens of precision sensors ensure every package contains the exact number of balloons. Nearby high-speed labelers print and apply brand designs, while the filling machines seal each colorful batch inside airtight plastic bags. The process ends as the finished packs slide down the conveyor, glossy, vibrant, and ready for global distribution. From the milky white drops of latex slowly flowing from the rubber tree, the same raw material can follow completely different paths, becoming a compact eraser that corrects every pencil stroke, or a thin, lightweight balloon that carries moments of everyday joy. And at the factory, we continue to trace those journeys, to tell the stories behind objects that may seem simple at first glance.